And what I like about our conference and its international character is that we can go from one part of the world to another. And now we're going to have a brief overview of AI and games that will be given by us by Associate Professor of Tandona, Engineering School of New York University, Julian Togelius.
Hi, everyone. I'm Julian Togelius, and I'm going to talk to you about artificial intelligence for games and games for artificial intelligence. So I represent New York University, where I'm an associate professor, and the startup Model AI, where I'm a research director. So actually, let's start with talking more about me, because I think it's polite to always introduce yourself properly to your audience. So I grew up in Malmö in Sweden, where I went to high school. And then I finished high school, which was surprising because I almost failed my mathematics courses. I was very bad at math and I hated it. I decided I did not want to become anything that had to do with math, definitely not some kind of engineer. So I started studying philosophy and psychology because I wanted to understand the human mind. As I did so, I realized that in order to really understand the mind, I needed to build minds, because philosophy didn't really have the tools I needed, and psychology wasn't going anywhere either. So I needed to build artificial intelligence. So I gradually switched over to computer science. I did a master's in England and a PhD in England. I worked in Switzerland under Jürgen Schmidhuber, and I was faculty in Copenhagen. Now I'm here at New York University. Basically, what I did was that I started out thinking that I would evolve neural networks, use natural evolution or artificial evolution to train settings for neural networks that could help me, that could control little robots. And then I got tired of robots, because robots break down all the time and you have to charge the batteries, the wheels get hot, all these kind of things. And I realized at some points that many of these experiments you do with robotics, you can actually do them with games as well. So for my PhD, I did a lot of work with evolving neural networks that drove racing games, racing cars in a racing game, and showed a couple of interesting things. But there's somewhere along that process, I realized that I could switch things around. Not only could I create AI that played games, but I could also create AI that help design games, that generated game levels and that modified the games, maybe in response to the player. And that became my career. So what I'm doing right now is that I work on making AI that plays games, maybe that plays games like a human player or that plays games in a particular style. But I also work on AI that helps making game better in various ways. So generating content, modeling players and so on. I make test beds for artificial intelligence, so that I make game environments where you can test your AI methods optimally. And I wonder about how this impacts AI in general. Basically, I use games to make AI better and AI to make games better. So I've been talking a lot about artificial intelligence. What is this thing we call artificial intelligence? There are lots of different definitions. One of my favorite definitions, because it's so boring and so dry in a sense, is that artificial intelligence is the quest to make machines able to do things which currently only humans can do. And this is what we've been seeing in a lot of different domains. We've taken a task that humans do well, but machines don't do well, like translating text or navigating streets with a car or something. And then we try to figure out how to make computer software that can do this. So making computers able to do things which are currently only humans can do. I was talking about games, which leads you to the question, what do humans do with games? If this was a live talk, I would ask you, the audience, what humans do with games. But you're not there in front of me right now. So let's think a little bit about this. When I ask people what they do with games, the first thing they say is that they play games. But play is only one part. Humans play games, obviously. That's kind of like the idea of it. But they also study them. I have lots of colleagues that are game studies scholars that come up with new ways of making games, understanding what games are about, and studying, like you study literature or history. There are people that build content for them, levels, maps, art, characters, missions, and of course people design and develop games. That's a big business, and so on. So all of these things are AI problems. Making computers able to do this are all interesting AI challenges. And it turns out that people always think about playing games as what you do with AI, but that's maybe not even the most interesting and the most relevant AI challenge. The other ones could be more interesting. But let's start with this, because there's been a lot of discussion about this. Video games being used as AI testbeds or AI benchmarks. So here we see several different video games that have been widely used as AI testbeds. There's StarCraft, the classic real-time strategy game here. You have a version of Super Mario Bros., the Mario AI benchmark. You have a racing game called Torx, and first-person shooter called Unreal Tournament. And these have all been quite widely used as for AI benchmarking. So let's look at what we have here. This is an example from the Mario AI competition, which we ran. I was a part of putting together this software back in 2009. The idea was that we had a competition where people would submit their best Mario playing bots, and they would play Super Mario Bros. Actually, what we used here is a freeware or public domain re-implementation made by Marcus Persson before he became Notch and became really famous. And we thought this was a really interesting AI problem. Then, just a week before the deadline, we see this agent being submitted. And this agent is fantastic. When we saw this, we were really, really happy because it's so fascinating. I know you're looking at this and being, wow, you see, mesmerized. You couldn't do that, right? But we were also kind of sad because we thought we had a really good AI problem. And then someone comes along and submits a bot that just solves it like this and plays, for all intents and purposes, a perfect game of Super Mario Bros., at least in these levels. And this makes you wonder, what can you actually learn from this? Is it that you had a hard problem and you thought it was easy? And as it turns out, it's hard to judge how hard a problem is for AI. Now, to add insult to injury, the method that was used here is something as simple as a star search. Basically, this method uses a very standard computer science method that you will learn in your undergrad, a star search. But it uses it not to plan a path in space, but to plan a path in state space. It does planning by copying the states, the full states of the environment, and trying to take different actions. So we thought a little bit about this and realized the A-star search had limitations. So next year, we developed a new version of this Mario AI benchmark, where you see you have these like little caves or something, where you have an overhanging roof. And all you need to do to solve this is to basically move backwards and then jump up on the roof again. And it turns out that A-star can't handle this. A-star is like a very sort of limited algorithm here that keeps searching right in front of Mario, but never moves back. So we sort of developed new levels of the same game, or a new level generator in response to this particular challenge. And then the challenge became much harder and had new different challenges. So instead, what we saw that year, 2010, was the winner of the competition is something called Realm. And this Realm agent is a combination of a lot of different methods. It uses an evolutionary algorithm to evolve rule sets, that decides where to go in a particular screen, and then uses A star to execute it. And it's the best Mario playing agent we know of. It is not pretty because there are so many things going on, but it plays a really, really good game. But then when you think about this, is this what we really want? Are we interested in an agent that plays the game as well as possible? Maybe a problem we should be solving is instead, how do we come up with an agent that plays as much as possible like a human being? This agent here, we actually developed a competition, which is kind of a Turing test, where you would have agent play Mario levels, and then people would watch them and try to judge which one was a bot and which one was a human. So this one here is an agent that was trained, a Bayesian network trained on my former postdoc's 5-year-old niece, which is played a pretty decent game. It's not the best Mario playing agent, but it looks like a human. Right, so we've seen a lot of AI can be used for playing specific games. Super Mario Bros. In particular has been used in this research field to a crazy amount. I mean, it's basically a very, very widely used benchmark. And the problem is that you develop your Super Mario Bros. Bots, and they can only play one particular game. They can only play Super Mario Bros. And that's a bit boring. You try to make them play a racing game or StarCraft, and you don't even know where to begin. The inputs don't fit, the outputs don't fit. I mean, it definitely doesn't have any kind of transferable skill. And the same thing, some very high-profile StarCraft bots like DeepMind's AlphaStar can really only play StarCraft, can only play StarCraft on certain maps, on certain versions of the game. They don't transfer at all. They certainly cannot play Super Mario Bros. Or a racing game. So it makes you wonder about, if you really want to develop real artificial intelligence, you would need to be able to play more than one game. You would need to be able to have some kind of generic, generalizable skill set, right? So we're going to get there. We're going to jump back in history a little bit, because in AI history, people have for a very long time been using games. So it used to be that in the beginning of artificial intelligence, chess was seen as sort of the epitome of intelligence. And people who started working artificial intelligence, here is John McCarthy, were often avid chess players, and they thought that to play chess, you need to be able to plan ahead. You need to be able to understand your opponent. You need to you need a lot of thinking skills. And if you can develop a computer program that can play chess well, then you could probably then you basically solve intelligence. And it turns out this wasn't true. Here we have Garry Kasparov losing against IBM's Deep Blue computer. This was back in 1997, and this was a huge sort of media event in all over Europe and the US, because we had a game that we thought was sort of the epitome of intelligence, and now we had a bot that could simply play it. And to add insult to injury, the software that played it was essentially a version of Minimax Search. Minimax Search basically means that you look at all the possible moves you can make, and then you look at all the possible counter moves that can be made, and so on. And then you calculate which is the optimal move, given that you want to optimize your value at every point, and the enemy wants to, or the adversary wants to minimize your board value at every point. There was a lot more complications to it, but this was the basic idea behind Deep Blue. And when you look at it, this is not artificial intelligence. This is just tree search, right? So people thought that maybe you needed another game. So you had Lee Sedol, was one of the world's best Go players. And here Lee Sedol is losing to Google DeepMind's AlphaGo in 2016. And this was another kind of big media event. We thought that Go, this classic Asian board game, which has a lot of different challenges compared to chess, would actually be a much better challenge. And it turned out that no, we can still make AI methods that play Go very well, better than a human, but they're still not generally intelligent. So the core method here is Monte Carlo tree search, which is another tree search method that uses statistics to build imbalanced trees so it can search deeper in certain paths. Anyway, we saw all these successes, and we're wondering, well, how does this help us bring artificial intelligence? If for any given problem, we can construct a computer program or learn a computer program that plays so extremely well, and yet it can't do anything else. It can't tie its shoelaces. It can't write a love poem. It can't cook spaghetti. It can't even play another game. So like the world's best game-playing programs are still extremely specialized. How can we construct an AI that can play many games? So one challenge we took on here was this, and we developed something called the General Video Game Playing Competition. So this is a competition where competitors submit AI agents, and the game engines lets these controllers play unseen games. So basically, the games that are the agent's going to be played were unknown to the developers of the agent when they were developed. So you can specialize a particular agent. So to do this, we developed the video game description language. The video game description language is a simple markup language that describes the kind of games you might have found in the early 80s. Games with 2D movement, graphical logics, and so on. And so here you see, like in the first part here, this defines what exists in the game. Here's a mapping from the level to these avatars in the game. For example, there's a diamond, and it's a resource, it has a certain shrink factor, and so on. And then you have the core rule set, the interaction set. What happens when these things collide? You collide with the dirt, then the dirt disappears. If a boulder collides with the dirt, then the boulder stops, and so on. And then in a termination set here, defines how do you win or lose the game. So what happened? This simple game description gives us a game that looks like this. This is like a little bit of recreation of the overworld of The Legend of Zelda. We have a human trying to play it. You need to kill the monsters, get the key, get to the door. It's not super advanced fare, but it's a decent game. And to show you that these are not obvious, here is what happens when a random player tries to win it. The random player takes random actions. So he is stupid. He loses. Now, what happens, what actually plays this well, is a version of Monte Carlo tree search. So Monte Carlo tree search was, the method that was at the base of AlphaGo. There was also a bunch of neural networks, but this was the base of it. And if you apply these problems, then you see much more interesting behavior. You still see some limitations because the Monte Carlo tree search doesn't always search as deep as it should. So right now, it can't find the door. Where's the door? I have the key. Where's the door? Help me, help me. Oh, there it is. Thank you. You win. And we saw that Monte Carlo tree search could actually, or versions of it with lots of modifications, could play a lot of these games, maybe half of them well. Not all of them. Here's Boulder Dash. This is a classic game from that I used to play in my childhood, so we had to recreate it. This is a game that has both action elements because you can get a boulder in your head, or you can be chased by these enemies, bats and scorpions and stuff. But there's also a puzzle element. How do you get to all these diamonds without getting fenced in, and where do you, or getting a boulder in your head and so on? So you need to dig carefully. Yeah, we're not going to follow up, but once you have these all these diamonds, you can make your way to the exit here. A random player obviously plays really, really badly and keeps digging away and gets smashed by boulders. The MCTS version we used here can solve it even. So in fact, we don't know of a good method that can play that can reliably win all these levels in this comparatively simple game. Now the point is, you could make a method that would play only Boulder Dash, but that would be kind of cheating. So we want like a generic method that can be applied to, we have like 160 games in this data set, but yet plays well in Bangladesh. And we don't have one, underscoring the challenge of actually playing games in general, not just coming up with a method to play one game, but playing games in general. And one question here is, if we had a method that you could just let play on the 100 top games on Steam or the Apple App Store or somewhere, and this method would simply win at all of them, and without having been tailored to any particular game, would this constitute general intelligence? I think it would. I think if you could win basically any game you gave it to, that was given to you, with some training time maybe, but without having specialized for that game, then you would have something like general intelligence. Anyway, now for something completely different. No, it's connected, but it's related. Let's talk about game development. Anyone here wants to be a game developer? The thing is, game development these days is a very sort of very labor-intensive process with a lot of people involved, and it's very specialized. And the biggest games are made by teams of hundreds, working over several years, costs hundreds of millions of dollars. Now, a large part of this is in generating the content. And there is a trend that has been existed in some games since the early 80s, which is procedural content generation, where some parts of the game content, the levels or like the settings and the quests and so on, are generated procedurally. So this is like here we have Elite, which is a game that was released back in 1984, and it has a huge world you can travel in, but everything fits into very, very small amount of memory you could have on your computer back then, because a home computer back then had about 1 million times less memory than it has now. But it had to generate worlds as you came upon them. And then there were Rogue, which was a classic game that also generated all the worlds as you sort of as you traversed them. So you have modern successors like Diablo series of games, which are very popular and involves no playthrough is the same because it generates the levels as you go through them. I recently played through Hades. It's a fantastic game. The same thing. Spelunky, which sort of kickstarted this revolution back in 2008. It's a platform game with ever-shifting levels. The thing is, you could play through the whole game in 20 minutes or so, but you probably won't because it's very hard. And every time you play it, it's a new thing. So you have to be good at the actual game, not just learn the levels. The Civilization series of games, also based on like that, you have a new world to investigate, to sort of explore every time. And No Man's Sky, a very famous game / art piece, whatever you want to call it, which has more planets you can ever discover, and all of them have unique fauna, unique flora, alien species, all these things. Everything is generated, and the game is bigger than anyone could ever explore. So we've been asking a lot of questions. I've been doing a lot of research on how can we make these procedural content generation techniques better. So for example, let's take an example. If we want to generate level of Super Mario Bros. So we want infinite Super Mario Bros. Levels. How would we do it? One thing we can do is use evolutionary computation. So evolutionary computation is a technique inspired by evolution in nature, where you have a bunch of individuals and you let the good ones survive and have offspring with each other, and let the bad ones die off. And you gradually sort of evolve your level in the search space towards the top. It's very effective. There are many different evolutionary computation methods, and they can be used in many different ways. So here you need to define a representation for this. So we defined a number of vertical slices, like little columns that you can split Mario into. Here's like column 1, 1 again, 2, 1, 3. And then we evaluated this. You use the fitness function, where you try to count the number of design patterns that would recur in these levels. And what you get here is a level generator that very quickly and reliably get you a lot of unique Mario levels. We followed up this work and came up with levels that would change in theme and difficulty across the level and so on. Can we take this further? Could we possibly generate completely new games? So I'm going to take a little older example from, not me, from a friend of mine, Cameron Brown. Cameron Brown developed this board game generator called Ludi, where he had rules for a lot of different board games. They were expressed in a Lisp-like language. This is checkers, Chinese checkers, 3 in a row, Gomoku, and so on. And then he had this process where he selected parents, crossed them over, generated a completely new board game rule, checked it was well formed, otherwise throw it away, gave it a name, tried playing it, optimized a game playing policy to play it well, checked it was drawish, or if it was inbred, otherwise evaluate. And he had a lot of fitness measures here. One of the fitness measures is how late in the game can you decide who's going to win? It's good if a game is unpredictable until fairly late. And this game, system, he ran this for a long time, and he produced a number of things, including something called Yavalath. This is the description of what came out of this. This is a game with 2 players, and you win this by getting 4 in a row, and you lose this by getting 3 in a row. And it describes which are the players and the tiling and so on. This is what it looks like in an abstract form. And this is what it looks like as a board game you can actually play. So, and you can buy it in a box. And it's fairly well reviewed. People like it. And it's clearly novel. No one had come up with this game before. It was designed by a machine. It was designed by a computer program. So it says here, Yavalath by Cameron Brown's Ludi. Interestingly, Cameron Brown didn't design this game. Cameron Brown just designed the software that designed the game. And still, Cameron Brown is selling it and getting the money. His software is not getting the money. Interesting, right? But I like this because it's proof of concept. You can actually generate a completely new game by a machine. Can you do this in video games? Yes, we've done some other examples. We have some work on this, but it takes too much to sort of go into here. So we talked a little bit about how the AI can build things. Let's look at a couple of other use cases here. One is like, can you collaborate with AI? So the AI can design levels and complete games, but you can do that too. So maybe you and the AI have different strengths and can work together. So this is what we see here. This has sound on. This is a game called Cut the Rope, which was popular a number of years ago. It's a sort of mobile game physics puzzle. You need to sort of move this candy around on these levels and feed the candy to the little monster down here. It's very fun. It's a long time since I played it, but it's a clever little game. So we thought, could you make a system that will help you design levels for this game, where you could add to the design, but so could the AI system, and you could collaborate. And this is the system we call Ropossum. So Ropossum can automatically generate levels. You press a button and it generates a completely new level. As you see here, they're all playable. It does this through a combination of evolutionary computation constrained by grammar and a form of depth first search constrained by prologue, which is a strange combination of methods here. So here we see a human make this game, design a game. He's putting all these little pieces in here, now he's putting in a bubble that the candy can fly in and so on, and we have a complete level. You can ask the system, is this playable? Yes, it is. And you see here at the top of the screen now, it's going to play this and also tell you what the reactions it takes. So it basically gives you instructions. And that was pretty nice. You can view the tree of actions it takes and try to understand what are the possible actions that could have been taken at each time. And then you can tell it that, okay, it's a nice level we have here. I want to keep some of the level, but I want you, the game, to change around to do some other things. All right, so here we have a new level. How is this playable? Well, you cut all of them in order. That wasn't a very fun level. Okay, so let's actually go back and get this level again and try to recreate a new level. And we have a playable level. How does this work? So here you play this by sort of putting the candy on the rocket, and the rocket goes into the bouncer, and then it falls off straight down, which is kind of surprising because this is not an interaction you would have expected in this game. So what happens here is that the system shows you a new potential interaction that you may not have thought of. It sort of refines your level by giving you new mechanics and giving a creative input in your design process. And I think this kind of tools have a bright future where you are working together with artificial intelligence and you get suggestions from the system, you get evaluations of what you're doing from the system, and you in general take turns to improve something. It's often called mixed initiative design. Okay, here's another use case. The other use case is generating tutorials. So you have games and you have levels for the games, but then you need to tell someone how they can learn to play this game. So, and this, of course, this kind of thing relates not only to games, but all kinds of interactive activities where you need to teach a human being how to do something, driving a car, and like, you know, making content or something like this. So here we pose the question, if we have a game, can we automatically generate a tutorial for this game? And we've been working on this for a while, and we have some new results, more than what I've shown you here. But the idea is that you reason in mechanic space, and you use automated playthroughs. So you use all these sort of game playing methods to play through the game, partly get agents, and then you sort of reason about which mechanics are active in the game and which need to be taught. So this is a system called at Delphi. So at Delphi here gives you it analyzes a game and tells you how to score points in the games, and not only tells you, like, gives you instructions for the different situations. It also gives you little examples how it happens. So it tells you, like, you know, you will gain a point if you have no key and you get the key, and then it shows you this happening in a little animation. It tells you how to lose, what are sort of the situation where you could lose, and how to win, and so on. So it breaks up. It identifies important mechanics it needs to teach you, and it breaks up the game in these parts and shows you these little examples. And there's a lot of ongoing work here. Things we really want to do here is like improve how to figure out what's important to teach in a game. And we also need to improve the game playing methods and so on. And we want to sort of make this relative to a particular player's playing style. All of this are quite complicated research problems itself. But they all interlock in interesting ways. Another thing we're working on, and this is we're particularly working on with the company I'm involved in, Model AI, is how to automatically test games. So this is a screenshot from what we call the glitch finder. The glitch finder uses exploration algorithms to try to find as many possible states in the game. And then it tries to find things like, do we have states where you're stuck in the game where you can't get out of the game geometry? Do we have states where the frame rate drops because it's too complicated to render? Do we have states where can you find shortcuts you shouldn't be able to find, and so on? And the idea here is that you can help game developers with this, because around 10% of a typical game production goes into testing. And it's very labor intensive. You need people to test everything, all the mechanics of the game and the content and everything. So this is another part of the game development process. Content generation is one, but testing is another part of the game development process where I think we can make a real difference by simply sort of automating or partly automating some of the process. So to conclude, as we close to the end here, talking about the relationship between artificial intelligence and games, I would say the video games are kind of the perfect test beds for artificial intelligence. I started in robotics, as I said in the beginning, and robots are expensive, they break down, they're complicated to service, and so on. Then you still need to design good environments for them and so on, which is even harder and more expensive. Here, video games are varied. They're cheap. You can run them. They're cheap, like both in terms of money and in terms of computation. You can run them really fast. They're designed to challenge the mind. Because, and this is something I haven't talked about yet, so a good game is designed to give you a set of challenges that gradually teach you to play the game. According to a set of theories, including by Ralph Koster, the famous game designer, these games are great pedagogical devices, and they teach you how to play them. So there's sort of a well-designed game is already an interesting cognitive test. And as game design progresses and we get more and more different types of games, this means that we're exploring the cognitive space available and finding new challenges. Now, to sort of reiterate the argument before, learning to play one game is interesting, but if you're interested in general intelligence, you need to be into general video game playing. You need to come up with methods of playing not just one game, but a bunch of different games. Now, on the other side, AI is the future of game design. So there are a lot of ways in which AI can improve the design and development of games. It includes testing games, which is going to help us out a lot. Generating content autonomously, generating levels or game logic or rules, or together with humans, depending on what kind of, what the use case is. Generating tutorials, modeling players, adapting player content, adapting game content to the player so that the game is perfectly adapted to a particular player, and so on. These things all go together, because in order to develop these game testing methods, you need to have good agents that can play the game, and also for evaluating content, which you need in order to generate content. So the game playing agents are really important because of that, including the general video game playing agents, because you may need to use them before you actually have finished developing your game. Now, at the same time, content generation in particular is crucial to coming up with interesting new challenges that help you develop better AI methods. So AI for games is not the same as games for AI, but they are crucially interconnected. So in this research field, typically one contribution to one of them is contribution to the other. Right. This was it for me today. I want to finish with a couple of recommendations. If you're interested in this, I have written a popular science book called Playing Smart on Games, Intelligence, and Artificial Intelligence. It's a relatively short read, and it doesn't really require many technical prerequisites. You can find it online from your favorite bookstore. It's from MIT Press. And also, together with my colleague Yorgos Giannakakis, who I've collaborated a lot with, some of the work you've seen here has been done in collaboration with him. We have this book called, simply called Artificial Intelligence in Games. This is a advanced undergraduate or graduate level textbook, which goes through a lot of relevant AI methods for games and a lot of different applications. It's available for free on this link, gameabook.org. You can also buy it. It's out with Springer, and you can get it as a physical book to read. So you may start with this one and then go to this one, depending on your levels of prerequisites. We also run an annual summer school on AI for games. That's school.gameabook.org. We have run it in Crete. We have run it in New York, and then we run it online this year. And hopefully next year we'll be running it in person again somewhere in Europe. and this will feature me and Yorgos and a number of other guest speakers. And that's it for me. Thank you very much.